Hi, welcome to the chapter Classification of AI and ML course for managers. So far in this course, we have discussed only the supervised regression problems like predicting housing prices in California or predicting the area burnt by the forest fires. Let's understand supervised classification problems. In classification, the algorithm learns from the labeled data given to it, builds the model, and then this model is used to classify new observations into classes. Let us see some examples. Say our task is to build a model which classifies the given image into fruits like banana, apple, and kiwi. Here we have labeled images for training the model. Each image has a label such as apple, banana, or kiwi. Since we have labeled data, such a classification will be supervised machine learning task. We feed these labeled images to the algorithm. The algorithm learns from these labeled images and builds the model. Then this model can be used to classify new images into one of the fruits. So, how does the training work? We first represent the image in tabular form, in the form of rows and columns. We will soon revisit how to convert an image into tabular form. Then, we split the data into training and test set in 80-20 ratio. And then, using training set, we build the model. And using the test set, we evaluate the performance of the model. And then we deploy the model in production, where it classifies the unknown new images into one of the fruits. Let's see one more example. Say we have to build a model which classifies the images into dogs or cats. Each image in the training set has a label such as a cat or a dog. We feed these labeled images to the algorithm. The algorithm learns from the features of these images and builds the model. Since here we are feeding labeled images to the algorithm, such a classification is a supervised machine learning task. Let's revisit the MNIST dataset from the topic representing data. The MNIST dataset consists of 70,000 small images of digits handwritten by high school students and employees of the US Census Bureau. As you can see, each image is labeled with the digit it represents. The MNIST dataset is considered the hello world of machine learning. Whenever people come up with a new classification algorithm, they want to see its performance on the MNIST dataset. Let's build a classifier or model using MNIST dataset, which classifies an image into one of the digits between 0 and 9. For example, here the model classifies the image as class 5. This type of classification is known as multi-class classification, where the model classifies the object into one of the multiple classes. How do we train such model? We have total 70,000 images in MNIST dataset. Now the question is, how do we represent images in the tabular form so that we can feed them to the algorithm? Also, what are the features and the label? There are 70,000 images in MNIST dataset, so the number of instances are 70,000. Each image has a label associated with it. Let's see how do we represent these images in tabular form. Each image in MNIST is of size 28 by 28 pixels. Also, each image is grayscale, or in other words, black and white. Such an image is basically a two-dimensional array of numbers. The black color is represented as 0, white is represented as 255, and other shades are in between. So, an image is a two-dimensional matrix of numbers. There are many ways of converting a two-dimensional image into one-dimensional array or list of numbers. For now, we will take a simple approach whereby we will append all the rows and make a single-dimensional array. A 28 by 28 image will have total 784 pixels, and it can be represented as an array of 784 numbers. So each row will have 784 columns, hence 784 features. The MNIST dataset can be represented in tabular form, where each row represents one hand-drawn digit, and value of each pixel in the drawing is a feature. Now we know the features and the label, and we have represented them in the tabular form. We feed this data to the algorithm, and algorithm builds the model. Let's simplify the problem for now and first train a binary classifier which classifies the given image into class 5 if the image is of digit 5, else into class not 5. A binary classifier classifies an object into one of the two groups. Let's name this classifier as 5 detector for now. As we have learnt, machine learning algorithms prefer to work with numbers, so we will have to convert features and labels into numbers before feeding them to the algorithm. Here, features are images, and we have already seen how to represent images in the form which can be fed to the algorithm. The output classes 5 and not 5 are not numerical. We will have to convert these two classes into numeric values. How do we convert classes 5 and not 5 into numbers? We can either use one-hot encoding or assign numbers to these classes. Let's assign numbers 0 and 1 to these two classes. 0 denotes the class not 5 and 1 denotes the class 5. Now the label also contains numbers. We can now feed features and labels to machine learning algorithm, and the algorithm will build the model for 5 detector. Then this 5 detector model can be used to classify the unknown images into one of the two classes 5 or not 5. Before training the 5 detector, the question which comes to mind is, how will we validate this model? Until we have a way to validate a model, we will not have confidence in the model. So, which performance measure should we use to evaluate the performance of 5 detector? As we have seen earlier, in the case of regression, the preferred performance measure is root mean square error, RMSE. Can we use root mean square error as the performance measure for classification? The answer is no, because root mean square error of say 1718 will not make any sense for classification. In classification, we are interested in classifying an object into one of the categories. Hence, we need different performance measures for classification. Let's see different performance measures for the classification task. In classification, one of the performance measures is accuracy. In the case of 5 detector, the accuracy is the number of images classified correctly. Here, total 2 predictions are correct out of 3, so the accuracy is 66.67%. Here is the question on accuracy. Say we have 3 images showing 4, 3 and 5. The 5 detector is some model which has detected 5 only in the second case. What is the accuracy of 5 detector in this case? Pause the video for a moment and calculate the accuracy. Here only one prediction is correct out of 3, so the accuracy is 33.33%. Though accuracy looks good in normal life, but it's not such a good measure of performance in classification tasks. Let's understand it with an example. Imagine we have a very dumb classifier which classifies every input image as not 5. Its accuracy for the given example is 3/4, which is 75%. Let's see the accuracy of this dumb classifier on MNIST dataset. In the MNIST dataset, around 90% of the images are of digits other than 5. Remaining 10% images are of digit 5. Since the dump classifier classifies every image as not 5, it will classify 90% images correctly, but 10% images of digit 5 incorrectly. So the accuracy of even this dump classifier will be 90%. This is simply because only 10% images are of 5. There is a huge class imbalance between the two classes, and such a dataset is called skewed dataset. If you always guess that an image is not 5, you will be right about 90% of the time. This demonstrates why accuracy in general not the preferred performance measure for classifiers, especially for skewed dataset. Let's see one more example. Let's say we have to build a model which predicts if someone has cancer or not. We have 100 people, out of which 95 people do not have cancer. 5 people have cancer. Say the model is very bad and predicts every case as no cancer. In such case, it will classify 95 non-cancerous people correctly, but 5 cancerous patients as non-cancerous. Now, even though the model is pretty bad at predicting cancer, the accuracy of such a model is 95%. This is because there are two classes, no cancer and have cancer, having 95 and 5 people respectively. There's a huge class imbalance and the data is skewed. This again demonstrates why accuracy in general not a preferred performance measure for classification, especially when your dataset is skewed. Let's see one more example. Say you have built the spam classifier which classifies the given email into spam or ham with 90% accuracy. Do you think this classifier is good? According to an analysis by Symantec in 2009, 90% of all the emails sent on the internet are spam. With this analysis, you know only 10% emails are not spam and you are dealing with the skewed dataset. Again, you will not trust this classifier on the basis of accuracy. Here's a question. Say your friend has built a classifier which classifies a given image as a male or a female. Your friend is really confident about this classifier as its accuracy is 90%. By now, you know accuracy is not a good performance measure for classification. What questions will you ask your friend to make sure if his classifier is really good? Pause the video for a minute and think about all the questions. You will ask what percentage of males and females images are there in the dataset. Your friend replies that in the dataset, 80% of the images were of males and 20% images were of females. Now you surely know the dataset is skewed and you will not trust a classifier. Let's explore other better performance measures for classification. A much better way to look into performance of a classifier is to look at the confusion matrix. The general idea of the confusion matrix is to count the number of times instances were correctly and incorrectly classified. Let's see the confusion matrix of 5 detector. The confusion matrix contains the counts of actual versus predicted value. Each row in the confusion matrix represents an actual class, while each column represents a predicted class. Each cell in the matrix represents the count. In this matrix, there are total 5 cases where non-5s are correctly classified as not 5s. Similarly, there are total 3 cases where 5s are correctly classified as 5s, while there are total 2 cases where 5 is classified as not 5 and 1 case where non-5s are classified as 5. If a dataset has 10 classes, the confusion matrix will have 10 rows and 10 columns. Here is the illustrated view of the confusion matrix. Let's understand the terms associated with the confusion matrix. True negatives are the cases in which images were correctly classified as not fives. It includes the cases where the actual images were of not fives and the model also classified them as not fives. False positives are the cases in which images were wrongly classified as fives. It includes cases where the actual images were of not fives but the model classified them as fives. False negatives are the cases in which the images were wrongly classified as non-fives. It includes cases where the actual images were of fives, but model classified them as not fives. True positives are the cases in which the images are correctly classified as fives. It includes the cases where the actual images were of fives and model also predicted them as fives. Though confusion matrix gives us a lot of information, but we require more concise metrics such as precision and recall. Let's understand precision and recall. In real life, precision is marked by lack of mistakes. For the 5 detector, precision is the measure that tells us what proportion of images that were classified as fives were actually 5. Here the 5 detector classified total 4 images as fives and it was correct only 3 times. So the precision is 3 out of 4. In other words, precision is about being precise. It measures how many classifications were correct out of all the classifications. So, if a model classifies only one image but classifies it correctly, then its precision will be 100%. In real life, recall means to remember something learnt in the past. For 5 detector, recall is the measure of what proportion of images that were actually 5 were classified as class 5. Here, there are total 5 images of digit 5 and the 5 detector classified only 3 of them as fives. So, the recall is 3 out of 5. In other words, recall is about classifying all the images of 5 as fives. Let's take one more example to understand precision and recall. Here the confusion matrix of the model which predicts if someone has cancer or not. Here the precision is the measure which tells us how many patients that model predicted as having cancer actually have cancer. Here model predicts that 110 patients have cancer, but out of these 110 predictions, only 100 predictions are correct. So the precision is 100 out of 110, which is approximately 0.91. Recall is the measure which tells us what proportion of patients who actually had cancer were diagnosed by the model as having cancer. Here total 105 patients have cancer and model predicts that only 100 of them have cancer. So the recall is 100 by 105, which is approximately 0.95. Instead of computing precision and recall every time we train a classifier, we prefer a single metric which combines both precision and recall. This single metric is called F1 score. F1 score favors the classifiers that have similar precision and recall. If between precision and recall one number is really small, then the F1 score will be closer to the smaller one. We have learned F1 score favors the classifiers which have almost similar precision and recall. But depending upon the problem, we may want high precision, high recall, or equal precision and recall. That is the case where we would want F1 score as our performance measure. Let's see some examples. Say we have to build a model which detects if a video is safe for kids or not. Would you prefer this model to have high precision or high recall for this task? Just take a moment and think what will be the meaning of high precision and high recall. High precision means if the model classifies video 4 and video 6 as safe for kids, they are actually safe for the kids. In high precision, we are okay if the model is not able to classify video 2 as safe for the kids, but whichever video it classifies as safe for the kids, they're actually safe. High recall means the model will try to maximize the number of videos that are classified as safe. In high recall, there might be chances that model will classify video 3 as safe for kids. This is because recall is about maximizing the ability to classify. So, question is, will you prefer high precision or high recall for this task? We would prefer a model which has high precision. It is okay if the model rejects many good videos but keeps only really safe ones, instead of having high recall and classifying a few really bad videos as safe for kids. Let's see one more example. Say we have to build a model which detects shoplifters on the basis of surveillance images. In case someone is marked as shoplifter, security guard would manually check. Would you prefer this model to have high precision or high recall? We would prefer the model to have high recall, even if the precision is low, because our goal is to catch almost all the shoplifters. In the high recall, the security guard might catch and examine some non-shoplifters also, but we will achieve our goal of catching almost all the shoplifters. Now, you may think that we can have both high precision and high recall in good model, but unfortunately, we cannot have both high precision and high recall at the same time. Increasing the precision reduces the recall and vice versa. This is called precision-recall trade-off. Let's understand this trade-off. For each instance in the dataset, the classifier computes a decision score. Decision score is decided by the classification algorithm. If the decision score is greater than a threshold, the classifier assigns that instance to the positive class, else to the negative class. Here again, the threshold is decided by classification algorithm. Here is the precision and recall values for 5 detector during the various threshold. As we can see, if we increase the threshold, the precision increases and recall decreases. And if we decrease the threshold, the precision decreases and recall increases. We can change the threshold as per our requirement. So how do we decide which threshold value to use? The answer is we can simply select the threshold value which gives us the best precision and the recall values for our task. Say for our task, we need high precision. Then we increase the threshold, and if we need high recall, then we decrease the threshold. Therefore, it is fairly easy to create a classifier with virtually any precision or recall we want. Let's say we want to achieve 90% precision. To achieve the same, we set the threshold to around 400,000. But in this case, we have only 18% recall. The high precision classifier is not very useful if its recall is too low. So if your boss asks you to reach 99% precision, you should ask him at what recall. Another way to select good precision recall trade-off is to plot precision directly against recall. As we can see, the precision drops sharply at 80% recall. We may select the precision recall trade-off just before the drop at 60% recall. But again, this entirely depends on your project. Let's understand one more measure of performance. For binary classifiers, the ROC curve, Receiver Operating Characteristic Curve. Before understanding the ROC curve, let's understand two more terms associated with the confusion matrix. Here is the confusion matrix of the model which predicts if someone has cancer or not. The recall is known as the true positive rate. The false positive rate is the ratio of negative instances that are incorrectly classified as positive. It is the measure which tells us what proportion of the patients that actually were not having cancer are classified as having cancer by the model. Here the false positive rate is 10 out of 60, which is 0.17. Now let's come back to ROC curve. The ROC curve plots the true positive rate against the false positive rate at various thresholds. We can use ROC curves to compare various classifiers. One way to compare classifiers is to measure the area under the curve. Higher the area under the curve, better the model is. A pure random classifier has the area under the curve equal to 0.5, whereas the perfect classifier has the area under the curve as 1. This was a brief introduction of various performance measures used in the classification task. Hope now you have a fair understanding of which performance measure to choose. Select the right precision recall trade-off that fits your needs and compare various classifiers using ROC curve and area under the curve. So far, we have worked with a binary classifier 5 detector. Let's come back to our original problem. We want to build a classifier or model using MNIST dataset, which classifies an image into one of the digits between 0 and 9. As discussed, this is multi-class classification. How do we train this multi-class model? There are two strategies: one versus all, OVA, and one versus one, OVO. Let's discuss these strategies. In one versus all, we classify 10 different binary classifiers, one for each digit between 0 and 9, like 0 detector, 1 detector, 2 detector, and so on up to 9 detector. While classifying an image, we pass the image to each classifier and select the best class predicted. Let's understand one versus one strategy using a very simple multi-class classification problem. Say we have to train a classifier which classifies an object into one of the three classes A, B, and C. In one versus one strategy, we train multiple binary classifiers, one for each possible pair of classes. As you can see, we have trained 3 binary classifiers for each possible pair of classes A, B, and C. Now to classify an object X, we pass it to each binary classifier and assign it to a class which has the majority. Say the AB classifier classifies object X as B, BC classifier classifies object X as B, and AC classifier classifies object X as C. Since here class B has the majority, our model will classify the object X as B. If there are 10 classes, the total number of pairs of 2 classes will be 45, which means we will have to train 45 classifiers. If there are 100 classes, the total number of pairs will be close to 5,000, which means there will be 5,000 classifiers that we need to train. Let's compare the two strategies. The main advantage of one versus one strategy is that each binary classifier only needs to be trained on part of the training set. For example, the AB classifier will get trained only on small part of the training set, which includes the class A and B. This saves a lot of time and computing resources as compared to training on full training set. Like with most approaches in machine learning, you should always rely on cross-validation or comparison of performance of both the strategies and take the decision based on that. Hope now you have a good understanding of how to train a model for multi-class classification problem. Let's understand one more type of classification called multilabel classification. In multi-class classification, the classifier classifies the given instance only into one of the classes. For example, a fruit can be classified either as apple or banana, but not both at the same time. On the other hand, in multilabel classification, an instance can be classified into multiple classes at the same time. For example, a movie can be classified into multiple categories. Say the multilabel movie classifier is trained on 4 categories, biography, drama, sports, and sci-fi. Then for the movie Raging Bull, such a multi-label classifier will output multiple binary labels, one for each category. Let's do hands-on and learn how to train a binary classifier using AzureML. We will train a binary classifier which predicts if someone has breast cancer or not. We will use breast cancer dataset available on AzureML. Log into AzureML, go to Experiments and click on Blank Experiment. Go to Samples dataset and drag breast cancer data to the canvas. This dataset consists of breast cancer diagnosis data against features from cell samples. Click on Visualize to visualize the data. The dataset has 683 rows and 10 columns. Here, class is the label and other columns are the features. Next, drag select columns in the dataset and join it with the dataset box. Click on Select Columns in Dataset Box. Click on Launch Column Selector and select all the columns. Next, drag Split Data and join it with Select Columns in Dataset Box. Split the data into training and test set in 80-20 ratio. Specify the random seed as 42. Type classification in the search box, and here you can see all the classification algorithms. Since our classifier is a binary classifier, let's select two-class logistic regression for now. Logistic regression is used to estimate the probability that an instance belongs to a particular class. For example, logistic regression can give answer to the question like, what is the probability that this image is of digit 5? If the estimated probability is greater than 0.5, then the model predicts that the instance belongs to the positive class labeled as 1, else to the negative class labeled as 0. Drag train model and join it with training set box and two-class logistic regression box. Click on Train Model box and specify label as class. Drag Score Model and join it with Train Model and Test Set. Drag Evaluate Model and join it with Score Model box. Now we are done with the steps. Let's run the steps and wait for the execution to complete. Let's visualize this score model step. Here we can see scored labels and scored probabilities columns. Scored label is the class predicted by the model, and scored probability is the probability predicted by the model. As you can see, if the probability is greater than 0.5, then scored label is 1, else 0. Next, evaluate the model. Here, we can see the ROC curve and precision versus recall. Below is the confusion matrix. Accuracy is 96%, precision is 97.8%, recall is 91.7, and F1 score is 0.946. Currently, the threshold is 0.5 and area under the curve is 0.99. We can change the threshold to achieve any precision or recall we want. For example, to achieve 96% recall, we can decrease the threshold to 0.43. As you can see, on changing the threshold, precision has also changed. This was the quick demo of how to train a model for classification task. To get a better model, try different algorithms, Select the best one and then tune its hyperparameters. Once you are confident with your model, deploy it into the production. Let's quickly revisit the concepts we learned in this chapter. We learned about how do we train a model for classification task. Then we started with multi-class classification problem. Then we learned various performance measures for classification task. We learned accuracy is not a good performance measure, especially for the skewed dataset. Then we learned about the confusion matrix. The general idea of the confusion matrix is to count the number of times instances of class A are classified as B, and so on. Each row in the confusion matrix represents an actual class, while each column represents a predicted class. Then we learnt about various terms associated with confusion matrix. Then we learnt about precision and recall. Then we learnt about F1 score, which is a single metric combining both precision and recall. Then we went through some examples where we require high precision and high recall. Then we learnt about precision recall trade-off. Increasing the precision reduces the recall and vice versa. Then we learned that we can achieve any precision and recall value by changing the threshold. Then we learnt about ROC curve and area under the curve. ROC curve can be used to measure the performance of various classifiers. The perfect classifier has the area under the curve as 1. Then we learnt about the two multi-class classification strategies, one versus all and one versus one. Afterwards, we learnt about multilabel classification. Finally, we trained a binary classifier to predict if someone has breast cancer or not. Hope you liked the chapter. Stay tuned for the next chapter and happy learning.